Hello. We start a new chapter in which we talk about power spectral density. Power spectral density is defined for a wide class of wide sense stationary random processes. The outline of this chapter is as follows. First, we will look at analysis of signals and LTI systems, and we compare the case of deterministic versus stochastic process, and we'll see what is not possible when you're dealing with the stochastic process. Specifically, for deterministic signals, we'll see that Fourier transform is well defined, but for stochastic random processes, the Fourier integral may not necessarily diverge. For such a case, we will be able to work on another approach only for wide sense stationary random processes. We also, as examples, we look at power spectral density of white noise. We look at a couple of examples on frequency conversion, and we'll see how we could use the concept of power spectral density as an alternative way to analyze linear time invariant systems. Remember that if you have an LTI linear time invariant system, the relationship between input and output is a convolution integral, which is also true for the case of stochastic processes, as long as the convolution integral converges. And finally, we'll present an important theorem which shows that power spectral density is having physical meaning. The learning outcome in this chapter is that we'll be able to analyze wide sense stationary random processes in frequency domain, analysis of them. You shall be able to do analysis of deterministic LTI systems when the input and output are wide sense stationary random processes. And using power spectral density, you will be able to characterize the jointly wide sense stationary random processes and LTI systems when they are interacting.